Okay, today we're going to talk about simple functions first. So simple functions are used to approximate measurable functions, and the simple function itself is defined in the following way. So we say the function f is a mapping from E to R bar. It's called a simple function. If this range of f under E is finite. So what that means is the f can only take finite many values. In other words, we can partition E into finitely many disjoint measurable sets. We call them E1, E2, all the way to EP. P is any natural number. Okay, can be arbitrarily large as long as it's finite, such that a function f of x is equal to the piecewise constant function, smaller c. Okay, so strictly speaking, we need to make these CIs distinct. But this is not very important. The point is that if we can write our function f as a weighted sum or as this linear combination of characteristic functions over the set E, where this characteristic function, I can think this in this way. Say this is E, then say we can partition it in some way. Then we have the E1, E2, so on and so forth. And on each piece, we have the function takes the value, corresponding value ci. So over the E1, it takes the value c1. Over E2, it takes the value c2. Okay. So we can definitely make these values distinct, but it's not really important. The point is that as long as you can write them in a finite summation, it'll be fine. Okay, as long as this is the finite summation, it'll be fine. Okay, so you can see that this is just a piecewise constant function, and that has different values. Supposed to have different values on different pieces, and these pieces are disjoint. Actually form a disjoint union, or this E can be written as a disjoint union of these sets. Okay, and apparently this function f will be measurable if all those sets E1 through EP are measurable. Okay, that's the only case we consider. We consider all these partition sets are measurable sets. Okay, now with this we can approximate a measurable function, a general measurable function, pointwisely using these simple functions. So that's the theorem we're going to introduce. Okay. So let's first consider non-negative measurable functions. So I can use this notation, means that the function f takes the value greater than or equal to 0. Okay. Suppose we have a non-negative measurable function f, then there exists a sequence of non-decreasing simple functions, such that this sequence converges to the function f pointwisely. Okay. So here's the proof. Okay, so this is a constructive proof. We just need to construct such for any given f, we need to construct such a sequence. So the idea is this: for every natural number k, we first consider the partition of, let's say this is the x. This is the one-dimensional case, but actually we can work this on n-dimensional Euclidean space. This E can be a subset in Rn. Okay, but I'm just drawing this in a 1D case. Okay, this is the y function or function value. So for every k, which is an integer, I'm going to partition this 0 to k into 2 to the k equal pieces. Okay, so they're just divide them to very small pieces, and each one of them has the length of k over 2 to the k. Okay, so here I will have 2 to the k pieces, and each piece, the length here, will be k over 2 to the, so 1 over 2 to the k. So each segment has the size 1 over 2 to the k. So in total, this part will be k times 2 to the k, this many pieces, right? Because in total length is k, and each segment is 1 over 2 to the k. So this is for the area from 0 to k, and everything above k I will just set to k. So what I'm trying to do here is to partition this 0 to positive infinity into interval 0 to k, and from the k to positive infinity, it should be, and then partition 0 to k into k times 2 to the power k equal sized intervals, in the sense of this j minus 1 or 2 to the k and the j 2 to the k for j from 1 to k times 2 to the k. Okay, and as you can see, each one of this interval has a length 1 over 2 to the k, and it's half closed, half open, and there are a total of k times 2 to the power k such intervals. Okay, so this is how I'm going to partition the y-axis or the value axis, and then I'm going to define I will define EKJ to be the set of points where the function takes the value in between j minus 1 over 2 to the k, f of x less than j over 2 to the k. That means all the points on the real line or in an n-dimensional Euclidean space such that the corresponding function value falls into the small band here, one of the small bands here. Okay, so that's EKJ. And apparently k is 1, 2, so on and so forth, and then j is 1 through k times 2 to the power k. Okay, and that's how I define the k. And also I'm going to define ek to be the set of points where the function f takes the value bigger than or equal to k, including infinity. Okay, so this is how I'm going to partition this the positive part of the extended real numbers into this in total, so the k times 2 to the k plus 1 segments. Okay, and now define the function a set of simple functions for each k. I'm going to define the simple function fk to be if the function f at x is taking value in between, or if x belongs to ekj, then I will take the lower bound, which is j minus 1 over 2 to the k, if x belongs to ekj, and I will take the value k if x belongs to ek. As we said, the x must belong to one of those one of these sets. So for each x, we're going to set up the value here. And as you can see, no matter which point I'm evaluating, this fk of x is always smaller than f of x. The reason is that if x belongs to ekj, then f of x is taking value bigger than or equal to this. Although it's not too much bigger, but it's bigger than or equal to this side. I'm just going to take the lower bound. And also here, the f of x is greater than or equal to k, and I'm just taking the function value k. So as you can see, this is a measurable. This is a simple function because we just consider the set. We just consider a partition of this domain into these types of sets, and on each set I'm going to give a value, a different value. And so this is a finite combination of them. As we said here, for each k there are only this many plus 1 of these sets. So there are finite many of these sets, and for each piece we only have a constant. So this is the f of k. And also, as we said earlier, the fk must be less than or equal to f of x, okay, for each point. Okay, so it's clear that fk of x is less than or equal to f of x for any x in E and any k, right? And also we can claim that the fk is non-decreasing. The reason is when k increases, we're going to get finer partition of this set. Okay, and once I get a finer partition, then each interval here will be smaller, and we're going to take a less rounding compared to the smaller k. Okay, so it's like previously where partition, say from from 0 to 1. We're just taking the value here or here. So if function is falling between 0 and 1, we just take 0. If it's bigger than or equal to 1, I will just take 1. And now, when k equals to 2, then I actually partition this into 4 pieces. And then if the function value is lower than 1/2, I take 0. If it's between 1/2 and 1, I'm going to take 1/2. So the function is, we get a finer refined partition of this y-axis. At the same time, we get a better approximation, or less crude approximation of the function f. And this fk is apparently non-decreasing. Okay, and also for any x, such that f of x is finite, we know that there exists, because it's finite, that means that we know there exists some k large enough, and the k is bigger than or equal to f of x. And in this case, there is f k x is still smaller than f of x, but their difference is less than 1/2 to the power k. Right? Actually, for this k and for any k larger than this, we know this is true. So when the big k is bigger than the f of x, we know this will be, for any little k, this will be less than or equal to 1/2 to the power capital K. And we know that this is approaching to 0 as k goes to infinity, right? So this goes to 0 as k goes to infinity. So I don't need to really write that. Okay, and for any x in E such that f of x is equal to positive infinity, then I know that my fk of x will be just equal to k, and apparently that is approaching to infinity as k goes to infinity. Right? So in either case, we can see that the fk converges to f. Okay? So now, in summary, what we have is for this given function f, we constructed a set of a sequence of simple functions in this way, so that they are kind of a lower bound for when you make a partition of the y-axis. They take the lower bound value for each function value, for each fx. So this is a sequence of simple functions, and they are always less than or equal to f of x. And this sequence is non-decreasing, and as k goes to infinity, this sequence f of k of x goes to the f of x at each point. Okay, so this proves the theorem. Now, Okay, so next theorem is a very simple extension of the previous one. Suppose we have a measurable function f, then there exists a sequence of simple functions we call fk, and the magnitude of sequence or the absolute value of fk is always bounded by the absolute value of f, and this sequence fk converges to f pointwise. And if you also know that this function is uniformly bounded by f by some number m, then we can actually show that this sequence of simple functions converge to f uniformly. Okay, it's a uniform convergence to f. Okay, so this is a notation for uniform convergence. So now let's see how to prove this. The first part is pretty easy. The idea is that we know we can consider f to be written as f plus minus f minus. And we know that both f plus and f minus are measurable, non-negative measurable functions. And we can apply the theorem before, the result before, to get a sequence converging to a sequence of simple functions that converge to this f plus. So I can call it fn plus. I can have a sequence of simple functions that converge monotonely to f plus, and also another sequence to the f minus. And you know these two do not overlap with their because you know if it's this f plus is 0, that means if f plus is positive, then the f minus f negative must be 0 there, right? Remember the example we saw earlier. Say you have this kind of function, then this is this part will be f plus, and when it's positive, then the f minus must be 0. So they don't really have overlap in their support. I think we're going to define the support rigorously soon later, but you can imagine the idea is that you have this f plus, like this one here, so I can just get a sequence of numbers, a sequence of functions like these ones to approximate this part, and it will stay 0 over this area. Okay, so now this is how we get this fn plus, and we can also get fn minus. In the taking the difference of these two will give us a simple function, and we know that fn plus has magnitude less than, which actually is positive, so it's less than or equal to f plus. Since we showed earlier, this is a non-decreasing function. It's a non-decreasing sequence of simple functions. And similarly, we know that this is true. And that is why when you take the absolute value, you're just taking the sum, right? So the fn plus fn minus is less than or equal to f plus f minus, and this is just the absolute value of f. And this is just my fn, absolute value of fn. Okay, if I set my fn to be the sum or the difference of fn plus and fn minus, then I know this. Okay, so that's actually just a simple extension of that. And apparently, fn plus converges to f plus, fn minus converges to f minus, so that's why my fn will converge to f. Okay, so the critical part is the next one. If we know the function f is bounded, then suppose the function f is uniformly bounded by m, then we know that for all the k bigger than or equal to m, I know that I'm going to make a very fine partition from 0 to k, in the sense that each segment has a length only 1 to the 1 over 2 to the k. So there is I would say, can say in this way. Then for any epsilon greater than 0, there exists k large enough such that it is bigger than or equal to this m, and also 2 to the power k is less than epsilon. Right? You can choose this capital K large enough so that both of them hold. And in this case, we can see that f k of x minus f x, we know their difference is less than 1 to the 1 over 2 to the power k, and if k is bigger than or equal to the capital K, this will be less than or equal to 2 over 1 over 2 to the power capital K, and that's less than epsilon. Okay, so we chose this k large enough so that we make sure that we can partition the interval 0 to k into small pieces, and also make sure that each piece has a length less than epsilon. Then we have this for all the k, for all the x, right? For all the x, and all the little k bigger than or equal to the capital K. And this means that the function fk, the sequence of function fk, converges to f uniformly, because for every given epsilon, we found this k large enough such that this difference is less than epsilon for all the k's. Okay, that is because this is actually fine approximation of the function f. Now, as I said, we're going to define the support rigorously, the support of the function rigorously. So the support of f is denoted by this here. So it's the support of f, and this one is by the closure of the following set of the set of points in X such that f of x is not equal to 0. Okay, it's a closure of this set. So you know when you take a closure, this becomes a closed set, no matter what this set originally is. Okay, so this is a closed set. You can also write this as, you just have this set and take a closure of this. Okay, either way. But this is a support is always a closed set. And if this set is also bounded, then it's a closed set and it's bounded. We know this compact, right? Then we say f has a compact support. Okay, so this is definition for the support of function. It basically means that the set where the function is non-zero, and take the and also include the limit points into that to form the closure. Okay, you can take an example. Say we have gk function to be the fk, which is a simple function we use to approximate a function f, and then we can multiply this function by a characteristic function of the ball centered at 0 with the radius x. So in this case, although the function is defined, although the original function f may not have a compact support, and as a consequence, the sequence of simple functions fk may not have a compact support either. But let's say that for each k, we'll only consider the behavior of fk within this ball. then it has a compact support. And since fk goes to f as k tending to infinity, and also k, this characteristic function tends to constant 1 as k goes to infinity. So this one will still be approaching to fk. Actually, it's non-decreasing. So actually, it's going to f pointwise as k goes to infinity. So here, the fk is a simple function. It's a sequence of simple functions such that the fk increases to f, non-negative function f. Okay. So we say that f is mapping from E to R plus. So it's a non-negative function. Okay. Apparently, this is still a simple function. If this is a simple function, because this is multiplying a characteristic function, and this gk is also approaching to f pointwisely. Okay. Now, with this definition of simple functions, we can consider convergence. Convergence of functions. Actually, there are different types of convergence, as we know. Before, if you have a sequence of functions, they could converge to a function pointwisely. And they can also convert to a function uniformly, which is even stronger. But here, since we're considering measurable functions, the behavior of the functions are really strange and can have very unexpected results. So we introduce two more different types of convergence. The first one is called convergence almost everywhere. Okay, so actually you can see this imagine the definition from the name. If it's converged pointwise, that means for every point it's converged. And the converged almost everywhere means that it's converged pointwise except over a measure zero set. Okay, so this is actually the definition. Okay, we use this notation. Fk goes to f almost everywhere on E if there exists a measure zero set Z such that fkx converge to f of x for all x outside of the C, outside of the Z. Okay, so this is the definition for convergence almost everywhere. Okay, so obviously you can see that if the sequence function f, k are all measurable, and then the function f here will be also measurable, because as we proved earlier, if it's pointwise convergence, then f must be measurable. But there's only measure zero set that the functions fk do not converge. So that doesn't really affect the result. And the f will be still measurable. Okay. Now let's consider a lemma. suppose I have the function fk and f. We consider the bounded set E. Okay, this is important. I will show this why the boundedness is required here. The sequence of functions converge to f almost everywhere on E. Then, for any epsilon greater than 0, we define the set. So this set is important. We're going to use this kind of notation a lot later in this class. So the ek epsilon is for every given positive number epsilon. I define ek epsilon to be the set of points where the function fk deviates from f by at least the epsilon. Okay, so this is where the fk is still a little bit far from f by the distance epsilon. Okay, so as you can see, for every given epsilon, I can define this subset of E according to the function fk. Okay, obvious. We can definitely observe that if the epsilon is smaller, then this set is larger, right? Because for smaller epsilon, we're going to include more points into this, and the original point will be still inside, but it's possible to include more points into this. So when epsilon gets smaller, this set could get larger. Well, at least not is increasing in epsilon. Okay, and the conclusion we're trying to make here is that there exists, for any epsilon, there is the limit of this kind of sets, where j is from 1 to, okay, from k to infinity, ej epsilon is equal to the upper limit of k of ek epsilon is equal to 0. Okay, so the lemma says that if I have a sequence if I have a bounded set E, bounded measurable set E, and I have a sequence of functions that converge to f almost everywhere on this E, then for any epsilon greater than 0, this ek epsilon will have an upper limit equal to 0. And this also implies that the limit of this measure of this set is equal to 0. Okay, the limit of this measure is also equal to 0. Okay, so let's see how to prove this. Well, we can see that if fk converges to f almost everywhere, means that they will converge to f pointwisely except for a measure 0 set. Okay, so let's say what are the points that the function does not converge over there. Say the function does not converge at x. Sorry. So we know that fkx does not converge to f of x if there exists a epsilon 0, and for all the k, there exists a little k greater than or equal to the capital K, such that fkx minus fx is bigger than or equal to epsilon 0, right? And as you can see, the similarity of this and this, so this actually means that x belongs to, we can say just for fixed epsilon 0, then therefore any k, there exists a little k equals to capital K, such that this set x belongs to this set, right? So in other words, just this. Okay. And we said that the points where the function does not converge, the sequence of function does not converge, is a measure 0 set. So that means we know that I can replace this exist epsilon 0 to exist some integer, right? So this means for I from 1 to positive infinity, I'm going to replace epsilon 0 by 1 over I. So there exists some 1 epsilon 0 means that there exists some integer or natural number I, such that this is a measure 0 set. Right? This means that the points where the function does not converge, or sequence of function does not converge, so this one should have a measure 0. Okay, and now you can see that for any, to prove the result here, they have this arbitrary epsilon. So for any epsilon greater than 0, we know that there exists a I such that this 1 over I will be smaller than epsilon. So in this case, if this is the case, then we know that Ek epsilon will be a subset of Ek over I. As we said, that Ek epsilon is decreasing, is increasing as epsilon decreases, right? Because first, as we said, for smaller epsilon here, this set is potentially larger. Okay, so we know this. We know this, and this means that for every given epsilon, we can find I such that this k from 1 to infinity, k from capital K to infinity of Ek epsilon will be just less than equal to the same one, but with 1 over I inside, right? And because this is a subset of this, so you take that, it will be the same, still a subset of the right hand side. So the measure will be bounded by the right hand side. And we know that this is just a, what, just a I apologize, this should be intersection and then union. Okay, let's say that I want this to be epsilon 0, just to specify the epsilon small enough, it will be fine. And then we know this is less than equal to the union of I from 1 to infinity, again k from 1 to capital, from 1 to infinity, and then union of little k from capital K to infinity of E k 1 over I. And we know that this is equal to 0, as we said earlier. This is equal to 0 right here, right? So now we know that this, if this is equal to 0 and this must be greater than or equal to 0, and that means this set is equal to 0. Okay. So this set is equal to 0. We need to see that so what we can claim is that this set is equal to 0. Well, now we know that this is just the upper limit of EK, right? It's just the lim sup of going to infinity in the EK epsilon. So this is actually this side here, this inequality here. Oh, just this. This is equal to 0. And how do we show this is equal to 0 as well? Actually, this is as you can see, this is always a subset of that. So if I define so actually just we can just, well, if you like, you can just we can just define this fk epsilon to be the union of this ek epsilon. Then you can see the lim sup of ek. For little k going to infinity, it's just the limit of capital going to infinity of this f capital epsilon. The reason is for larger for capital K increasing, this is just a monotone sequence of sets, right? Since if x decreasing sequence of sets, when k gets larger, we're taking the union of fewer sets, so this fk will decrease. So it's a decreasing set, and we know that originally the set f, the set E is bounded. So that means fk as a subset of E is also bounded. And we showed before that if I have a fk bounded, then the limit can exchange with the measure. It's big K. So this is equal to the measure of the limit of K going to infinity f capital epsilon. And we know this is the limit lim sup of EK, of mu EK. Sorry, mu of lim sup of EK. This is mu of the upper limit of EK. This is just by the equality above. So this should be, as we said, this should be equal to 0. And you look at this one, according to our definition, the fk epsilon is just this thing. So I just replace that here. And this is the left-hand side, is this. I just use the different notation. I use the little k here and the capital K this. So this is capital going to infinity, this little k, and this is little k. Okay, so that's how we got that. So actually you can see that it must be because the lim sup is equal to 0. The upper limit is equal to 0, and that causes the left-hand side to be 0. And we use the we exchange the limit and this mu because the set is bounded, right? Recall that this is required when we consider a decreasing sequence of sets. If it's increasing, then we don't need to have that. Okay. So next result, we're going to prove the we can use the theorem we just proved to prove this so-called Agarov theorem. I think sometimes it's also called Agarov. Okay, called this theorem. So what the theorem says is that if we have a sequence of functions that converge to f pointwise, converge to f almost everywhere, and then this, and also this E is bounded, then we can actually get this almost uniform convergence. I'm going to expand this so later. What does it mean by almost uniform convergence? So suppose we have this function f. There are all mappings from E to R, and we need this E to be bounded. Okay. If fk and f are finite almost everywhere on E, and also fk converge to f almost everywhere on E, then for any delta greater than 0, there exists a set E delta such that the measure of E delta is less than delta, and outside of this E delta, the function fk actually converges to f uniformly. Okay. So you actually can, when we look at the claim here, it's actually pretty strong. We have measurable functions. We know that measurable functions can behave very strange. Right? It doesn't have to be continuous. It can be really weird functions. But as long as that we have a bounded set, and all those functions are finite almost everywhere. Okay, basically except a measure 0 set, these functions are finite, and this fk converge to f almost everywhere. Then for any delta, we can get a subset of E, which is almost the same size as E itself. The difference is only this E delta, and the size of this E delta is less than delta, such that for this site, almost like the same size as E, the function fk is uniformly converged to f, not just the pointwise, but also uniform convergence. Okay. So to prove this, we first realize that we are going to use the same notation as before for any delta greater than 0, and for any I that is natural number, I'm going to denote this E k over I as the set of points such that fk minus fx is bigger than or equal to 1 over I. So this is the same as we did before. Okay, and now remember that for each of these sets, the limit as k goes to infinity, the limit of this set has the measure of this sets converge to 0. Right? This is what we proved previously. So that means mu of ek over I converge to 0 as k goes to infinity. Okay, so let's say just we choose this k large enough so that this measure is bounded by delta over 2 to the power I. So we know that by the theorem above. There exists a index. We call it, because it depends on I, we call it ji, such that, as we showed earlier, this limit will go to, this limit is 0. So we just say that I want this to be, this ji to be chosen sufficient large so that the union of k from ji to positive infinity of ek 1 over I want this measure to be less than delta over 2 to the I. Okay, so I can choose my ji large enough so that this is true for every I. Okay, and now let's define the E delta to be the union of these things. So I said that the I is from 1 to infinity, and for each I have this ji. So if ji, k is from ji to positive infinity of this set, ek I here, then we can say is that this delta k must have a measure less than delta. The reason is the measure of the E delta is equal to the measure of this set. Okay, and because of the subadditivity, this is less than or equal to the sum for I from 1 to positive infinity of the measure of the k from ji to positive infinity of ek 1 over I. And I know that each one of them is less than delta over 2 to the I. So this is just less than the sum of delta over 2 to the power I. And as you can see, the delta is a common factor, and the rest sum to, it's a geometric sequence which sums to 1. So this is less than delta. So now I know this, when I define my E delta in this way, then the measure of E delta will be smaller than the prescribed delta. And now let's see what happens on the complement of the E delta. So the E delta complement is just the E minus E delta. And according to our definition here, this is just this is E delta. So the complement of this E delta is just complement of this. And now you know that just can change the intersection to the unions, to the union to the intersections. We have y from 1 to positive infinity, and then the k is from ji to positive infinity of ek 1 over I complement. For each one, I'm going to take complement. And I write it out. This just means that I is from 1 to infinity, k is from ji to positive infinity, and we have this ek 1 over I complement. Recall that this is the ek 1 over I, and this is where the point is greater, the difference is bigger than or equal to 1 over I. So if it's complement, that means where the difference is less than 1 over I. Okay, so now let's see what this set actually is. This is a set where for, as we used the trick before, for any I or for any 1 over I, and for any, there exists some ji such that for any k bigger than or equal to the ji, the fkx minus fx is less than that. So this is exactly the definition for uniform convergence, right? It's for any I, or in other words, for any epsilon greater than 0, and there exists the ji such that the fkx minus f of x is less than 1 over I for all k bigger than or equal to ji, and for all the x in this E minus E delta. Right? This is actually what it means. So the function f k actually is converging uniformly to f on this E minus E delta. So we construct this set E delta, which has a measure less than the prescribed delta, and outside of this E delta, the function, the sequence of functions converge to f uniformly. Okay. So I'm going to make a few remarks about this theorem. So the first remark I'm going to make is the boundedness of E is important. Okay, we can take counter examples. For example, if I have this function f kx that is defined as characteristic function over the interval 0 to k. So let's just say that the function is fk is from R to R, and it's defined as characteristic function of 0 to k. Then, as you can see, this fk converge to 1 everywhere, right? Will converge to 1 everywhere. Let's just say that from R positive to R positive. So it's converged to 1 everywhere. But we cannot find any E delta such that the function f is converged to 1 uniformly. The reason is, as you can imagine, so let's say this is 0. So the function f, the limit should be constantly 1. But f1 is just this part. So it's 1, 2, 3, 4. So f1 is just this function. It's 1 over when it's less than, when it's between 0 and 1, and 0 everywhere else. And this is function f2 and function f3. Okay, so although we have pointwise convergence, but this sequence is never converging to f uniformly, because no matter how large the k is, there will be always the later part that is 0, that is different from the limit function 1. So this is the one example. The other one example is I just draw it here. So let's say I've defined my fk to be just the k times or x over k. So this is the straight line that pass through the origin with slope 1 over k. Okay, so when k gets larger and larger, this line gets flatter, right? The slope is getting smaller, so it's like this. When k gets larger, and you have this. Okay, again, you can see that for each point, you look at every point is converging. The sequence fk converge to converge to 0, right? For every point. But the sequence of functions will never converge to 0 uniformly, because no matter how large the function, how large the k is, when the x goes to infinity, there's the gap between the fk and 0 is getting larger and larger, right? No matter how small the k is, when x goes to infinity, there will be still gap. There will be still some gap. Okay, so that's what the first remark. The second remark is, although that we don't have the same result for the case where function is unbounded, but for the function that is, but if it's indeed unbounded, then we can get something weaker than that, or it's a modification of that. Then we can show that for any m, we can find a set EM such that the measure of EM is larger than this m, such that the function fk still uniformly converging to f on EM. So that means, although we cannot guarantee the same thing as in the Agros theorem, but we can find, you just name a size of the set. We can construct a set. There will be a set with, so we can name a number m, and there will be a subset em that has a measure bigger than this m, large enough, so that this function is uniformly convergent on this em. Okay, and the idea is simple. We just need to, if you have this measure, if you have this prescribed measure m, then we can construct a subset of E. So we can actually get this E by taking the union of the B, say B0 K, taking the union of this set B and this E. And you know that when K gets larger and larger, this will just converge to the set E. But for every fixed K, the intersection of these two will have a finite measure. But since the measure of E is infinite, so when we know that when K is large enough, this measure will be bigger than M. Okay, let's say it's bigger than M plus delta. And now I call this to be my Fk. So you choose the K large enough so that it's bigger than M plus delta. Delta, you can name it arbitrarily. So you can get this Fk. And then this Fk has a finite measure. Okay, it has a finite measure. For fixed K, it's bounded. And then for this Fk, we can apply the Agarose theorem. And then from this K, we can find a subset. We call the E. Because the EM is a subset of Fk, such that the measure of their difference is less than delta. That means the size of this EM is at least capital M, right? Because the sum of these two, is equal to Fk, and is bigger than that. And this part itself is only less than delta, so this part must have a measure greater than M, and the function Fk, the functions Fk will converge on this set uniformly. Okay. That's the second remark I'm going to make. The third remark is that it's also easy to get a sequence of sets. So we said that for every delta, you can find this E delta, such that this the function is uniformly converging on this E delta. But now I can say that for each j, the integer, I can have this ej that is basically like the E where the delta is equal to, so where this delta j is equal to 1 over j. So I know that the function f, so the ej has a measure, I'll say this is the complement of that. So the ej has a measure less than large enough, so that the difference between E and ej is less than 1 over j, and the function fk is uniformly converging to f on this ej. Okay, we can definitely do this, and then you can see that taking the union of these ej's, you're taking the union of these ej's, the complement of them will still be empty. The reason is this is just equal to the mean, it's less than equal to the E minus any individual ej, right? Because this contains this. So when we take it out, you get a larger set, and this is less than 1 over j, and this is approaching to 0. So that's why this one here just has a measure 0. Okay, we can construct a sequence of ej's whose measure is getting closer and closer to the E, in the sense that the difference of these two is less than over J, and the Fk is uniformly converging to F on each of these EJs. And this union of these EJs will have the same measure as the E itself, or the difference between E and the union of the EJs will be just equal to 0. Okay, so that's the third one. Another one remark I can make is that the we can actually restrict, we can also even consider the set E to be closed. Remember that here we show that there exists E delta such that the measure is small enough, it's less than delta, and this Fk convert to F on this outside of this E delta. We can actually even restrict ourselves to some closed set. So I want this to be closed. So the idea is that, remember that we, for any set like this, we can find some F that is closed subset of this E minus E delta. We know that for any measurable set, we can find some closed subset such that the measure of this E minus E delta minus F is also less than delta. Okay, and in this case, we can see that over this F, the function is still uniformly converging because it's uniformly converging to this larger set. It must be converging to the subset on the subset, and the measure of this F is close to this one. The difference is only delta. So you take out the E delta and take out the F, so it's like taking out the union of them. Okay, and this, as we said, this is a you take out this, it's less than 2 delta. Okay, it will be less than 2 delta. So over, sorry, it's also less than delta, but you can just say that the mu of E minus delta will be less than 2 delta, and this F is closed. This F is closed, and the function Fk convert to F uniformly on this F, and that is and the F has a measure that is close to E, in the sense that difference is less than 2 delta. And apparently you can make this delta to be half delta, and all the delta to be half delta, and then eventually here you just don't have the 2 here. It's just you just find a closed set F whose distance, or who is large enough so that the difference here is less than delta, and the sequence Fk convert to F uniformly on this closed set F. Okay, if you like it to be a closed set, but that's but in general, as you can see, that if you can show that for arbitrary set, it's easy to get a closed set. You're just adding one more step. So we can change right? So just remove a small portion of this, so to keep the closed set left, and you can merge that the small portion you removed from this, merge that into this, so that the measure of this thing is still smaller than the delta or 2 delta, as we showed earlier, and this one is closed. Okay, that's the last remark I want to make.